In this section, I'm going to talk about work energy equation, which is going to be quite useful in solving usually complicated dynamical problems. And you are going to see why it is useful in many complicated dynamical problems and why it makes them much easier. So we need to start with the definition of the work. Um, Based on the definition of the work, which is quite just a definition, if we have a force, any force, and let's say we are applying this force to a mass and this mass is moving on a path. The definition of the work for this force, work of force F during the movement is which we show it with du is going to be equal to F dot dr, and r is the displacement of this force. So if it moves just a little bit with the length or with the magnitude of dr, so dr is the displacement of this force, then the work of this force over this displacement is going to be F dot dr. We need to dot product the force to the vector of the displacement. And this is pure definition. And if the force, let's say the force moves from one point like 1 to another point like 2, and during this movement the force, the magnitude, and also the direction of it can change, then the work of the force from 1 to 2 from point 1 to point 2 will be the integral of this equation. So integral of du is going to be u, and we show it with u from 1 to 2, which means the work of force F from point 1 to point 2 is going to be equal to the integral of F dr, starting from 1 and ending at point 2. So we need to start from 1 and end at 2. That's going to be the definition of work. And this work has some properties that I'm going to introduce them to you, which are going to be helpful for us later. First of all, you can, if you want to calculate this work, one of the things you can do is, let's say this is the force. We can split this force to the components of it in the tangential and normal direction. Let's say this is the tangential direction at this moment, and also this is the normal direction. So if I split this force to the components of it in the tangential direction, let's call it Ft, and also the components of it in the normal direction, let's call it Fn, then the work from 1 to 2 is going to be equal to, let's say this is point 1, this is point 2. Based on this equation, it's going to be F dot dr, and we can write F as Ft in the et direction plus Fn in the normal direction. So we are going to have Ft in the et direction plus Fn in the normal direction. Dot product to dr. The displacement is always in the tangential direction. We don't have any displacement in the normal direction. Because of that, I can write dr as the magnitude of this vector dr. So I'm going to show it without any vector sign, times et. So this is all together is the vector dr. Now if I do this dot product, the dot product of et to et is 1, the dot product of et to en is 0 because they are perpendicular to each other. And because of that, this integral is going to be just ft times dr from 1 to 2. So what's the meaning of this? As you see, there is no Fn here. It means if you have a force which is perpendicular to the direction of the movement, which is perpendicular to the path of movement, in other words, it's not going to do any work. So this is one of the important results. Fn, normal force to the path of movement. Doesn't do any work. Which is a very important property. Another point, so let's call this point 1, this is point 2, or note. We can do another thing to calculate the work of the force. For example, again, based on that equation, the work of the force from 1 to 2 is equal to integral of f dot dr. If you know your force in Cartesian or xy coordinate, you can write the force in terms of fx and fy, in terms of I and j. So I can write the force as the component of the force in the x direction, which we need to multiply to I hat, plus component of the force in the y direction, j hat. Dot product to, we can always write dr as dx in the I direction plus dy in the j direction. Now, when we are doing this dot product, you need to know I dot I is 1, I dot j or j dot I, they are 0. And also j dot j is 1. Because of that, this integral is going to be equal to fx dx plus fy dy. So if you know the components of the force in xy coordinate, then you can calculate the work of fx separately and calculate the work of fy separately. So this is equal to the force in the x direction times dx plus integral of the force in the y direction dy. They're going to be totally independent from each other. That's another important point to know. For example, let's say we have a box here that we are applying force P to this box. And this box is going to move from here to here. Let's say the direction of the force is theta from the horizontal direction, and always is going to have this angle from the x-axis, and the displacement is d. Now, what is the work of this force? During this displacement from here to here. So based on that equation, u from 1 to 2, u of this force. We have other forces here, right? We can have friction, we can have gravitational force. I'm not talking about those forces. We can calculate the work of those forces separately. Here we are talking about just this force. I want to calculate the work of only P. Based on the equation that we just derived, it's going to be equal to the integral of the force in the x direction, which is P cosine of theta, times dx. And I'm assuming P is constant, it's not changing, plus force in the y direction, which is P times sine of theta, times dy. So let's put the coordinate here. This is x and this is y. So during this movement, the integral over x moves, if x changes from 0 to d, so the limits of this integral are going to be 0 and d. For this one, which we have dy, y of this point is 0, y of this point is 0 as well. It is 0 all the time. So we are going to have integral from 0 to 0, which is 0. And also, in other words, you know, the perpendicular force, the y component of the force, it is always perpendicular to the direction of the movement, so it's not going to do any work. And this integral is a simple integral because p cosine of theta is constant. We can take it out of the integral. And 0 to d dx is going to be just d. So the result is going to be p cosine of theta times d. As simple as that. Another important point is about conservative forces. So what is a conservative force? You are going to see at the end of this section. I'm going to show that with an example. Let's say we have a particle at this point, and we have gravitational force on it, mg. We can have other forces too, but here I'm going to talk about the work of this gravitational force. And we are moving this particle from here with this weird path to here. So at the beginning, let's say it is here, and at the end, it's going to be here. And I want to calculate the work of gravitational force from here to here. So how can I do that? Based on the equations I just derived, work of gravitational force from 1 to 2 is going to be equal to integral of fx dx plus integral of fy dy. X component and y component of the force separately. And the x component of the force, the gravitational force, is 0. It doesn't have any component in the x direction. This is x and this is y. And also the y component of the force is going to be negative mg. So fx is 0 and fy is negative mg. So I'm going to have negative mg times dy. Here we are doing integral over y. Y of the first point, let's say the height of this point is y1 and the height of the last point is y2. So we are going to integrate from y1 to y2, which is of course is going to be negative mg times y2 minus y1. So this is going to be the work of gravitational force. What is interesting about this equation, the interesting point is this equation is totally independent from the path of movement. It doesn't matter if I move this particle over this path or maybe some other path like this, right? At the end, if I calculate the work of gravitational force, it's going to be always dependent to the position of the first point, to the height of it, and also to the height of the last point, y1 and y2. And the rest of it doesn't matter. These kind of forces that in which their work is totally independent from the path, we call them conservative forces. We are going to have only two types of conservative forces in this course. Gravitational force, which I just showed you, it is conservative because the work of it is independent from the path. And the other one is going to be spring force. Before moving to the spring force, something from your physics. If you remember, you called mgh, you call it potential energy or gravitational potential energy. Here I showed you U from 1 to 2, the work of gravitational force, is equal to mgy1 minus mgy2. Mgy1 is the potential energy at the beginning. I'm going to show that with V1. So I'm going to use V as potential energy. So U from 1 to 2 is going to be potential energy at the beginning minus mgy2, which is going to be the potential energy at the end. This is another important equation, which I'm going to use it in a few minutes. Let's talk about the spring. And before that, V for gravitational force here is mgh. And sometimes we show it with Vg, which means potential energy for gravity. For a spring, let's say we have a spring and the stretch of it is x. So if the end of a spring is here, the stretch of it is going to be equal to 0. So let's say this is the beginning point, and I am moving it from this point, for example, on this path over here, then bring it back. Whatever you want to do, you can do on it. And at the end, it comes here. This is x1, the initial point, and this is x2. And I want to calculate the work of a spring force. So at each moment, if you, let's say for example, the end of the spring is here, the force of the spring is gonna be k times x in this direction. So the work of it at this moment, I need to multiply to dx to calculate the work of it, right? Or based on the equation that we learned in the previous page, u from 1 to 2 work of the spring is going to be equal to integral of fx dx. Fx is going to be kx in the negative direction, so negative kx, times dx. And the initial point is x1 and end point is x2. And this integral is a simple integral. It's going to be negative 1/2 of k times x2 squared minus x1 squared. Again, as you see, this work, the work of a spring force, is totally independent from the path of movement. If I grab it from here, bring it here, then here, then here, then bring it here, it's going to do the same work as if I move it here, then move it here, then bring it back. So it doesn't matter how it moves, the work of that spring force is going to be totally independent from the path of movement. It only depends to the initial point and final point. Because of that, spring force is a conservative force. And also, if you remember from physics again, the potential energy of the spring, which I'm going to show it with Vs here, is 1/2 of kx squared, which x is the stretch of it. And here you can write this, the work of the spring force, as 1/2 of kx1 squared, which is v of the spring at 1 minus v of the spring at 2. So for both of these, for both spring and also gravitational force, the work of them is going to be the potential energy at the beginning minus potential energy at the end. This is true for all conservative forces. And actually, that's the definition of the potential energy. It comes from here. That's another important point to know. Now, I'm going to add all of these together and derive the work energy equations that we are going to use for the rest of this section. Work energy equation. Let's say we have a particle. Again, it moves from here to another point, from 1 to 2. And also we have a bunch of forces on it. In this section, or in this part, I'm going to consider all the forces that we have on this particle. In all the previous steps, I assumed we have only one force, or I calculated the work of only one force. Here, I'm going to calculate the work of all the forces that we have in our system. So the work of all the forces from 1 to 2 is going to be equal to integral of sum of all the forces dot dr, the displacement from 1 to 2. But we know some of the forces based on Newton equation is mass times acceleration. Let's say the mass is m. So this is going to be equal to mass times acceleration times dr. And acceleration, you can write it in tangential direction and normal direction. You can split it in those directions. So this is going to be equal to integral from 1 to 2 of mass times acceleration in the tangential direction, et, plus acceleration in the normal direction, en, dot dr. And we know dr, the displacement, is always in the tangential direction. So I can write it as the length of displacement dr without any vector sign times e tangential. And if I dot product these two together, I know the dot product of et to et is 1, et to en is 0 because they are perpendicular to each other. So this is going to be equal to integral from 1 to 2 mass times acceleration in the tangential direction times dr. But there is something magical here about this equation. We know, if you remember, we know at is equal to v dot. And at is equal to v dot. And also, if you remember, we said at dr, or we called it ds over there, but it doesn't matter, it's just a name, is equal to v times dv. We have this time-independent equation for general motion, right? So I can replace at dr with v dv. So this is going to be equal to mass times v dv from 1 to 2, 0.1 to 0.2. And why I did this, because we know what is the integral of v dv, right? Because we have only one variable. Here we had two variables, dr and also acceleration in the tangential direction, which is changing all the time. So we couldn't do that integral. But after changing it to v dv, now we can do the integral. An integral of v dv is going to be 1/2 of v squared. From 1 to 2 is going to be 1/2 of velocity at the end squared minus velocity at the beginning squared. So this is quite amazing. The work of all the forces that we have in a system from point 1 to point 2 is going to be dependent to the velocity at the beginning and also velocity at the end. And also, again, if you remember from physics, 1/2 of mass times velocity squared, we call it kinetic energy. And here we show it with T. The kinetic energy is 1/2 of mass times velocity squared. So the work from 1 to 2 is going to be the kinetic energy at the end, T2, minus the kinetic energy at the beginning. So the total work on a particle is going to change the kinetic energy. That's the whole point here. And also the other point, which is quite important, and it's going to give us the final equation, that you need to know that final equation, and we are going to use probably only that equation in the rest of this section and in all the problems, which is U from 1 to 2 is combination of the work of all the forces that we have here. So if you separate all the conservative forces that we have here, like work of spring and also work of gravitational force, and write them as V1 minus V2, the difference between potential energy, and if you have any non-conservative forces, show the work of them with U prime. So here we are going to have V1 minus V2 plus U prime from 1 to 2 is going to be equal to T2 minus T1. And if you rearrange that, we are going to have T1 plus V1 plus U prime from 1 to 2 is equal to T2 plus V2. This is the main equation that we have here, which we are going to use it in almost all the problems. So what is this? T1 is the kinetic energy at the beginning. V1 is the potential energy, combination of gravitational potential energy and spring potential energy at the beginning. Plus U prime from 1 to 2. U prime from 1 to 2 means work of all the non-conservative forces that we have in our system, like for example friction force or external force, anything which is not conservative in our system, is going to be equal to the kinetic energy at the end plus potential energy at the end. And this potential energy again is combination of all the potential energies that we have, like spring and gravitational potential energy. Next videos I'm going to show you how to use these important equations, this important equation, work energy equation, to solve fairly complicated problems.